This program is brought to you by Stanford University. Please visit us at stanford.edu.
All right. So we're getting on this pharmacokinetics kick that we're on now. We're going to be studying modeling the human body with regard to the fate of a drug that you may inject or have maybe someone injects it in you when you're not looking. And of course, the concentration of the drug with respect to time will rise in your blood or plasma. And then it drops. And it drops because either it is being metabolized or you excrete it. All right? Now, most all drugs have what's called a lethal threshold, and that is if the drug concentration rises above a certain plasma concentration, sometimes for very short periods of time, other times longer periods of time, then you croak. So if someone sticks you or you take an overdose of drug, maybe they can get you to the hospital before it reaches the dotted line and have some kind of interventional therapy that would keep the drug from passing over this dotted line, therefore not reaching the lethal threshold. And this is generally done with some form of what's called dialysis, which is either, there's a couple ways you can do this. You can actually hook this machine up to your blood supply, run the blood through this machine. The machine removes the drug, puts the clean blood back in your body. And so the drug concentration almost reaches it and doesn't quite reach the lethal threshold, and then it might drop down. Why might it do this?
You unplug the machine?
You unplug the machine at this point, and then the drug goes up, but you haven't stuck yourself with a needle. Can you imagine why that might happen?
Just depends on where you're looking. It might redistribute.
Exactly. It depends on where the drug was distributed. So this is measuring the concentration of the drug in blood. And so it rises in the blood, you turn the machine on, it drops, you turn the machine off, the blood concentration rises. So that must mean the drug had gone into some tissues. And now when you turn the machine off, that drug is coming out of the tissues back into the blood. And so that has to do with the rates at which these things happen. This is called rebound. And this can be really pretty bad. Because let's say, hey, we're there. We get this thing, turn the machine on, bring it down. Hey, guy's fine. Let's go have some coffee. You turn the machine off. Meanwhile, the rebound happens, takes it way up here. You come back, the guy's splayed out like a dead fish. All right? Because you missed it. Because the drug, particularly fat-soluble drugs, will go into the adipose or fat tissues and sort of get stored in there, and then they'll come out, but they come out slowly. Red?
On the first breath, why does it continue to go down after it gets below the lethal threshold, or lethal threshold? Because wouldn't he stop metabolizing it when he dies?
No, he's not dead.
Okay.
Oh yeah, you're right. I mean, if he dies right here, then it would just probably be a flat line. That's right, unless it was draining out some orifice. It'd be just a flat line. Yeah, right. So presumably the area under this curve, the concentration of drug for this period of time didn't kill this guy. Good point. All right. I thought it was kind of macabre to show death. All right. So now the idea is, how do you model mathematically the human body so that you could in fact simulate the behavior of drugs infused into a human? And a lot of what we do in chemical engineering is to make mathematical models that simulate physical events. Because if you can get a model that's reasonably accurate, you can imagine you can do all your experimentation on a computer. And you can learn a lot about a system. But of course, the system's only as good as the model is in describing that system. So one of the things you might think about is, well, let's model ourselves as a tank. All right, and see this thing here? That's a stir bar. See? Stirring the tank. And the tank has a volume V. And there's a flow rate of Q, sort of gallons per hour, if you will, of material entering my tank. And it has a concentration of some solute in it. Could be the drug. That's C0 of T, meaning that the concentration of drug could, in fact, vary with time coming into the tank. We fix Q in this case. C1 of T is the concentration of the drug inside the fluid in the tank at any given time T, and the fluid occupies volume V. And since this is well mixed, because we have a stirrer in here, the fluid that's leaving the tank is also C1 of T. Now, what this allows us to do is have a time-varying concentration of solute, I'll call it, or drug in the input stream, and we have a response of this system, C1 of T, in the output stream. So what's going to be different about this mass balance in any that we have done in the class so far is this mass balance is not at steady state. So this is your first non-steady state mass balance, in which case input minus output is equal to accumulation. Now, we don't have reaction in here, but let's imagine I had reaction. In the case of this being a drug, what would the reaction correspond to? Yeah? Go ahead, somebody. What can happen to the drug? Two things. Metabolize it. Metabolism is chemical reaction. So I could have a term here of chemical reaction which would represent loss of the drug in here by metabolism. And input minus output is the input minus the excretion, and then the accumulation of the drug inside the tank or inside your body. Now, I don't think any of us would like to believe that we can accurately sort of physically mimic ourselves mathematically as just a tank with a stir bar. Maybe a dugong, but certainly not one of us. So let's take a look at the time-dependent mass balance. It basically says, what's this term here? What does this represent? The what? Speak to me, people. We've got a lot to cover. You got to work with me here. So it's the volumetric flow rate of stuff coming in times the concentration of the stuff coming in. What are the units of that? Grams per time, pounds per time. So this is the amount that's coming in. And do you see it can be time dependent? Because if C0 changes with time, then the amount coming in is going to change with time. Minus, what's this term? Here it is, the stuff coming out is equal to, what is this?
Storage.
Storage or accumulation. So C1V represents what?
Stuff inside.
The stuff inside the tank, and it's changing with time. So you get the ddt of C1 of V. Since V is a constant, I can take it out. C1 is the dependent variable. It is the variable that we're searching for to solve. T is the independent variable. C0 of T will typically be specified. Q will be specified, and V will be specified. And knowing those, we can integrate this equation, the primal urge, to compute C1 of T. So here's the differential equation. It's a first order, ordinary differential equation. And in order to solve this, I need an initial condition. You need to tell the equation where the system is starting. So what's the initial condition? One could be is that the tank is initially free of drug. It's just a fluid of volume V, has no drug in it. So C1 at t equal to 0 is 0. And then at some time t greater than 0, I turn this on and I start putting drug into the tank. And what do you think if you had to draw a plot of concentration versus time, C1 versus time? What do you think that would look like? Someone draw it. Just do it. Do you think it would do this? No, it would. Do you think it would do this? You think it would do this? So it would rise and then plateau out. So you have an idea of what this should look like. We'll work this problem for a situation in which the input stream concentration, C0 of t, is just a constant. We won't get fancy yet and say that it's a function of t. It's just some constant value of drug in this stream entering at flow rate q, being removed at flow rate q, and the problem we want to solve is what is C1 of t? So you see something like this, the primal urge, integrate. So you shift the variables over, you integrate, you get a log function. This is of the variety of x dx. This is why you took math 0. You integrate it, and the solution is C1 of t is equal to C0, which is the concentration going into the tank, times 1 minus the exponential of minus q times the time, whatever time it is, divided by the volume of the container. And if I plot this for a given value of q and v, I get a curve just like you guys drew, and ultimately C1 approaches, as you might expect, C0, the input concentration. And then it can't get any higher because that's all you're putting in. Now let's take a different problem. The tank, I don't mean is initially empty, but what I mean is the tank is initially empty of drug, C1 of t equal to 0, the same thing we did before. So this is the problem we're going to work. However, we're going to say that the inlet concentration is equal to a constant for t less than big T, and after some time, big T, I don't turn off the flow into the tank, but I take away the drug. So there's no more drug in what's coming into the tank. So C0 drops to 0 abruptly at t equals big T. Can someone draw what you think that one's going to look like? And I'll let you see if you can guess. If I were to plot C1 of t versus t for this example, where does it start? Starts, there's nothing in the tank, and then here's big T. So what happens?
Goes up.
And what is this value up here?
C0.
So it grows, it goes, it goes, it goes, it goes, and what happens? Boom. So that's what I would expect the solution to look like. I have a constant C0 up until sometime t, I shut it off, and down it comes. So let's solve that problem. First of all, we make the mass balance. We have the same differential equation. The only difference here is what you're telling the differential equation to respond to in terms of inputs to the system, the so-called initial conditions. Well, so we already solved, didn't we, this part of the problem? We just solved it. There it is. But we now know at some time t equal to big T, we shut this off. So we have to solve, if you will, the back end of the problem. And the back end of the problem has a different initial condition, doesn't it? The back end of the problem has the initial condition is that the concentration reaches this point and you turn it off and you expect it to drop. So how do you do that mathematically? Well, you say the initial condition for the second half of the problem is that at time t equal to big T, C1 of t, the concentration in the tank, is equal to what? Well, it's just equal to this with t replaced by big T. All right? So that's the concentration that is reached after time t. This is now the initial condition for the second part of the problem. So now I solve my little differential equation, and I use that as the initial condition for an input value C0 equal to 0. And so the differential equation, so it becomes a little bit more simplified because C0 is 0. And you can verify for yourself, if you integrate it, that the C1 of t becomes equal to this expression. So let's talk about this answer to see if this makes sense. So here's C0. This is what was in the stream. And here's big T, 1 minus e to the minus q big T. And here's e to the q 1 minus big T over, or t minus big T over v. So first of all, you check, does this make any sense? So we know at time t equal to 0, what should the answer C1 be?
0.
So if I put t equal to 0 in here, what do I get?
E to the 0 is 1.
So I get what? 0. Okay, so that check. Whenever you solve a differential equation like this and you get an answer, always go back and check that it satisfies the initial conditions that you put in it. Because if it doesn't, it's time to change your major. You got that. All right. Now let's ask the other question. What happens at time equal to big T? Put big T in here. What do you get for C1? Yeah, you get the initial condition for the second half of the problem. C1 equals C0 times 1 minus e minus q big T over v. Remember, that was the initial condition that started this problem right here. And so the other thing I can check is T what? T becoming, I expect as T gets very, very large, remember I've shut off the drug, what do you expect to happen in your tank eventually? Concentration will reach 0. So let T go to infinity, what happens? What does C1 become? 0. Becomes 0. This exponent is going to drive this function to 0 because this is a constant. So this looks right. And so you have an exponential rise on this side. You have an exponential decline on this side. And now you've solved your first, what we call, problem in dynamics. You've solved an unsteady state mass balance, and you've predicted with this the time course of the change in concentration in this tank. Now you can see you could take this and do some really interesting things. You could have 2 tanks connected, or 3 tanks, or 4 tanks. And that starts to look like a what when I start connecting all these blocks together?
The human.
The human. All right, you could have a tank that represents the leg, and one that represents the mind, and one that represents the nose. Whatever you need, to sort of decide what really describes a human. So we have the hope, you see, of describing the fate of a drug in a system. Now, did you notice on that last plot that I plotted concentration versus time in dimensional terms? But if you took this class, what do you really want to cast that? Because imagine on this thing, look how silly this will get if you hadn't taken this class. If I said, this plot had to be made for a particular value of what? T, Q, and V. So what does that mean? For every value of Q and V that I can possibly think of, what does that generate? A different plot. I now have as many plots as there are pages in Google to describe my little tank. Terabytes, attobytes of information. But you took this class, and you found out if you do what to this, how might you reduce the number of plots? Make it what? Dimensionless. So let's make it, and how do we do that? Look at this. Here's all the dimensional terms we have. C1, C0, the input, Q, the flow rate, V, the volume, big T, the time, and little t, the running time. Okay, here's the key. To make something dimensionless, if I want to make concentration dimensionless, I would have to divide it by something that has units of concentration to give me something here I'll call C star, which has no dimensions. And so the question is what constants do I have in my problem that I can look to normalize my dependent and independent variables? That's the key thing you want to ask. I've got my dependent variable, which is C1, and I've got my independent variable, which is time. How can I combine any of my given parameters in such a way as to create parameters that have the same units as either concentration or time that I can use to normalize, that is, non-dimensionalize these variables? Do you see that C0, which is the input concentration to the tank, which is given, is something that's given in the problem? If I divide that into C1, the concentration is a function of time, my dependent variable, I get C star. C star has what dimensions? It has no dimensions. I can take real time t and divide it by V over Q. V over Q were two parameters in this problem. And V over Q has units of what? Time. And therefore, I have a little t prime here, which I could take my big value of t and divide it by V over Q and get a dimensionless time. So if I take my solution, so I want you to look at the solution of the first problem we did and convince yourselves that this is so friggin' dysfunctional. You know, they don't make parts for these things anymore. I don't know. You can read it. This is dimensionless concentration versus dimensionless time. And this is the equation I plotted. Do you see that this equation is the same as the equation? In fact, someone read it to me. For the first part of our solution, it was, what was it? It was C1 of t is equal to what? C0 times what? 1 minus what?
E to the negative.
E to the minus QT over V, right?
Yeah.
So do you see that if I take C0 and divide it over here, I get C star is equal to 1 minus, and what is this Q over V? Q over V is, when I divide Q over V into T, I get T star, right? So this is 1 minus e to the T star, which is what I have right here. Do you see, I can make a plot of this, T star versus C star, without telling you what? You don't have to know, do you have to know Q and V to make that plot? No, you don't. You have one plot. It starts at T star equal to 0. C star is equal to 0. As T star goes to infinity, C star approaches 1. That's dimensionless. Now, if I were to ask you, after 10 minutes, what is the concentration in the tank? What would you need from me to use this plot? You need what? You need
the flow rate, the volume, like all that.
You have to ask me for V and Q because I need to put 10 minutes into T. I need to do what? Divide by the V over Q that I give you, which gives me a what? A T star. So now I can come to my T star plot, and I come over here, let's say it's T star of 2, and I come over here and I read a C star of 0.84. How do I turn the 0.84, which is dimensionless, into something that has dimensions? Multiply by C0. So embedded in this, which was attobytes of graphs, in one graph is everything you need to know. And all you need from me is what is V over Q, or what is V and what is Q. And I can then use this to recover all the data for any V over Q combination that you want to give me. If I take the last example we did, where we turn on we start putting stuff in the tank and then we turn it off and it drops, you see the curve is just about, it looks just about the same as it should, but this is C star versus T star. Now, in order to use this plot, do I need more than one plot? Say I only need one plot to describe the whole system. Does one plot work here? Here's what's plotted. This is just the dimensionless form of the answer we just got. Will that one plot describe all the possibilities? Or are there other plots? And if so, why are there other plots, if there are other plots?
We'll need different plots for different C naughts, right?
I can recover C1, for any C naught that you give me, just like I could here. I can recover any time for any V over Q you give me. But what's the other thing that's unique about this problem that's not here?
The big T.
The big T. You see big T sitting right here? It's T prime, actually. It's the dimensionless big T. So obviously, when I plotted this, I had to plot it for a particular T prime. So because of that, I will have as many plots as I have T primes I want to explore. But I've still reduced the number of plots by an enormous amount. So you see, in this particular case, I actually had 4 parameters, which I was able to collapse into, took one of the parameters into here, the C0. I took 2 of the parameters into here, the V over Q, but I had the big T left over. So this plot is actually for a particular big T prime. But it's still a huge reduction in data. It will always be a huge reduction in data. You should check that this representation in dimensionless terms is what you would expect to have gotten when you non-dimensionalized the problem solution that we got in the second part. But I think if you just compare the two and look at them, you'll see. This is the what does this actually represent, if you will? This happens at what T star? When T star is equal to what? What puts me right here? Big T prime, right? When T star is equal to big T prime, C star is this. This is, in fact, the peak, isn't it? And then as T star keeps running, it pulls it down, just as it did in the solution that we got on the previous page. And so if I put this up here, see, this is cool because you can't do this in PowerPoint. You see what I just did here? I superimposed 2 things with my hands. And I didn't have to go back to PowerPoint and work for 4 hours to figure out how to get a transparency overlay with the right, just happened magically like that. And there it is. There's our solution in dimensional terms. Here's the solution in dimensionless terms. And so I have only this one plot for the particular T prime that I chose. How did I get it? I just divided C1 by C0. For QV over T, I put in T star T, the ratio, divided it into big T, and I got T prime here. So that's how you non-dimensionalize answers. Now, can you think of how I could have ended up with these plots right off the bat? What would you have done at the beginning of the problem? What's the differential equation? dc1 dt equal to what?
Q over V. Q over V. And it's going to be C naught minus C1.
I don't know. What was it?
Over V
Q over V.
times C naught minus C1.
C naught minus C1 of t, right?
Yes.
What could I have done here? And what was our, let's do the first one. The initial condition was what? C0 equal to what? The big C0 constant, right? That's what we solved. At when? T equal to what?
Less than.
I'm solving the first one. I'm doing this. So it's t equal to 0, right?
So yeah.
What could I do to this that would allow me to get to here right away? What would you do to this? This equation is in what form dimensionally? Do these have dimensions? C, T, do they?
Yeah.
Yes. So how could I transform this equation?
Q over V times dt could be dt.
So if I bring this around and absorb this into the t and get t star, I can actually write a dimensionless form of this equation of what do you think it would be? You help me with this side. What did I have to divide through to get this? C0, right? So then what does the parentheses become? 1 minus what? C star. Or T star. And what is the initial condition for C star?
Zero.
Remember that first problem is a constant coming in at C0. That's the constant. So this is the constant. This is the value. If I divide one by the other, I get C star equal to 1 at T star equal to 0. So if I non-dimensionalize the equation and the initial condition before I solve it, I will directly integrate this and get this equation right here. So the point is, I did this first just to get you comfortable with non-dimensionalization and how you do it. But in fact, if you start with a differential equation and non-dimensionalize it, you'll get a non-dimensional answer. So the preferred way of solving these kinds of problems is to write them down in their physical terms using the equations that are available to you, and the equations will all have dimensions. Then once you get your equation set, then you come back, you non-dimensionalize it, and then you integrate the non-dimensional form. You know, doesn't this look a lot easier to do? Because you get rid of all the parameters. You know, they all go away. They all get wrapped up in here. These are all the constants in the equation. You don't have them floating around. So that's a little added benefit. Now this all may seem, well, sort of obvious, but what you've seen is a couple of really important things today. One is that you can do an unsteady state mass balance now, You know how to put reaction in it. If there's metabolism, you just add another term on the accumulation term. You end up with a first-order ordinary differential equation. Now, why do you end up with a differential equation? What drove us to the differential equation? Why did we end up with that? We hadn't had it before. It's not steady state. See, the things were varying in time. Integrating the equation tells you how the concentration changes in time in response to the initial conditions that you basically told the differential equation or the mass balance. The equation ensures you're conserving mass, but it doesn't know what mass it needs to conserve until you tell it how much mass is coming in and when, and that's what we did with the initial condition. And then it responded. Yeah?
Sorry, I was wondering why C star is equal to 1 at times equal 0. Because I thought C star was C1 over C0. Isn't that?
It is, we're getting the zeros mixed up here. This is the concentration. We called it C0, I think, didn't we, when I set the problem up. We just said, let me go back, I'll get it for you. It's a good question, I know if you really look, you'll see I actually changed the subscript, but it doesn't show up very well in the drawing. So let's put that back up. Do you see that right here? C0 of t is equal to C0. C0 is some constant. And when I divide this through, C0 of t divided by this constant, which we call C0, is C star. C0 is the constant that I'm using to normalize concentration with. This C1, this could be, remember this could be a function of time, this input. And then I said, let's make it a constant and call it C0. Does that?
Where does C1 go when time goes 0? Because I thought C1 at time 0 is...
That's the concentration in the tank. C1 is the concentration in the tank, and saying that C1 is equal to 0 at the beginning is the same as saying what is C star at the beginning in the tank. Oh, okay. I get what you're saying. Yeah.
0 divided by some...
Yeah, no.
Is it 0 divided by a constant 0? That's right.
This is, yeah. This is. But this is the concentration, the input stream concentration, having this constant value. In other words, I've got to tell the tank what's coming into it. If I said 0 was coming into it, what would the solution be? It would, if I never put anything in the tank, I'd get 0, right? So that's the reason C star is equal to 1. Because if I had picked C star, if I say C star is 0, in other words, if I pick this constant value coming into the tank as being 0, then the tank as initially has nothing in it. It will never have anything in it. That's another solution to the problem. It's not a very interesting one, but it's another solution to the problem. Now, imagine I have this problem. Say I had 2 tanks, and they're connected like this. So I have some stuff coming in, I have some stuff coming out of this tank, and then these 2 tanks are connected with 2 different volumes. Or let's say I was taking some stuff out of this tank, maybe even putting some stuff into this tank too. You can solve these problems. You just make mass balances just like you do around this unit, around that unit, and you'll start generating the differential equations that you need to solve in order to arrive at solutions that describe the dynamics of that kind of an interesting tank system. I can connect lots of tanks together, and eventually, you see, if you start looking at this starts looking like a chemical plant. And now, instead of making steady state mass balances, you can make unsteady state mass balances. So, to give you an example, let's say you have, let's say a petrochemical plant making polyethylene. A steady state mass balance tells you how the plant's going to operate when all the transients have gone away. But let's say you change the feed stream into that plant. So you put a perturbation into it. What happens in all the units downstream? Do they just sit there and stay the same? No, they all adjust. They all adjust to that transient. And if you think about the way a real plant operates, it's always typically running in some transient form. You're always sort of tweaking it, changing it, and so you really do need to understand unsteady state mass balances because that's the way the world works. And when you shut the plant down, everything starts dropping, and you need to know what's going to happen in each of the units. And the reason you need that is because you'll have other calculations going in. Let's say you have a reactor and you shut it down. You want to be sure that you shut things down in the proper order so you don't get hot spots, so you don't blow the plant off the face of the earth, and a lot of other things that could go wrong. And so you can simulate these very complex processes with these unsteady state mass balances. And so that's why we spend a lot of time thinking about them. But I can give you some really cool problems if I wanted to, right? With all kinds of things going on in these. So here you got an input here and an output, and an output, and these two tanks are connected together, and they can be two different volumes. And I can have a different kind of input here than I do here, and then ask you what's the time dependence of the concentration in this tank and in this tank as a function of time. And so right away we can get some pretty complex systems. So what we'll learn next time is we in fact will build a model that has several tanks, 4 to be exact, and that will be our human. And that will become you. And then you'll be able to play with you on the computer in our computer project and see if you can save yourself from a drug overdose. All right? Looking forward to it. We'll see how many save themselves and how many don't. What we generally do is the people that save themselves get to sit here in the front, and the people who don't sit in the back. And it's like sitting in the corner, you know, when you're a kid. And you'll be back there for a while.
The preceding program is copyrighted by Stanford University. Please visit us at stanford.edu.